Hello. I've never had my intro stolen by myself before. So you're all here for content. I hope I won't disappoint you. As I said in my pre-recorded intro, what I wanted to talk about was our progress to try and automate the process of machine learning, something that lots of people are trying to do. But we have a particular take on that, which I want to share with you and hopefully will be of some useful insight. So the goal is an automated AI workflow, beginning to end of the AI process, and to make that so that the human intervention is minimized so that you have to do the least yourself, both in terms of effort and injecting kind of prior knowledge and expertise. But for us, that's not really the goal. We have a much wider goal, which is to automate the entire computation workflow. And for us, the machine learning AI aspect is just one small part of a wider domain of computation. And we've been building out this goal for 30 years, where computation for us includes things like classical statistics, but also differential equation solving, or solving graph theory problems, or natural language processing, all of these different types of computation. And we want to try and make them all fit together into one coherent platform. And if we can succeed at that, then machine learning and sort of other AI techniques can just fit into that wider framework. And the central thesis of my presentation is that the answer to all of this is symbolic computation. And that having embraced the idea of symbolic computation, that actually has really surprising and useful benefits for doing things like machine learning. Even though anyone who knows how machine learning works internally, in the end it's a numeric operation. It's all kind of matrix arithmetic, number crunching at the kind of lowest level. But at the top level, where you interact as a human, symbolic computation actually really opens up AI and makes possible some of the automation that we're trying to deliver. So I need to take a digression here, a little bit off topic for the conference, but I promise I'll come back around to machine learning in a minute, and I need to explain what I mean by symbolic computation. And anyone, and I know a few people I've spoken to over the last day here at the conference have said, oh yes, I use Wolfram for my physics degree doing calculus problems. And for most people, symbolic computation is computer algebra. It's doing sort of maths equations and symbolic integrals. So I thought I'd start from that point of view and show a kind of really simple computer algebra type operation. So what we're doing here is we're taking a little chunk of maths here, this square root of 1 plus x over x squared plus 3x cubed, and we're doing a change of variables. We're swapping out the symbol x for the symbol u minus 1, well, the composite expression. So that's really kind of basic computer algebra type operation. The maths doesn't matter. It's to illustrate that this is made possible because behind the scenes we have this symbolic representation of that maths, that it's a bunch of nested functions in a kind of APL-like structure, where you could imagine representing this in something like XML or JSON, where we have symbols like times and power and plus, and they nest together to represent this expression. Now, it happens to be that we know what plus means as a symbol, that 1 plus 1 equals 2 and so on. But actually, from an abstract point of view, these are just, could have been anything. I could have had a symbolic expression like t of y plus u, and it doesn't know anything about those symbols, so it just holds that as a symbolic object. Now, why this is useful is that once you've got an operation like replacement that can apply to abstract symbolic things, well, then you can apply that to very different kinds of symbolic expressions. So I tried to think something as different as possible from some maths, and here's a 3D laser scan of my face. So this is a very sort of CAD-type object. If I can find my mouse here, you'll see that, which way do I need to face? This way. So this is my face. Not at all like a maths expression, but because this symbolic operation of replacement doesn't care what the thing is, it can operate on that to replace all of these triangles that represent the scan and to replace them with lines to make a wireframe version. So abstractly, what we've got is the ability to process anything that we can represent symbolically. And it turns out that, the ability to represent things symbolically is incredibly flexible. So you've seen this sort of maths representation, and I guess this was a 3D graphic, so this is behind-the-scenes representation of that picture. But data, whether it's key-value pairs or numeric arrays, these can all be represented symbolically as well. Other kinds of objects that you might want to process, like graphs. And crucially, things like code and things like a representation of a neural network can be represented symbolically. So now we've got the benefit starting to pop out, that we've got the ability to process and handle any kind of data the same way. And when you have things that are a mixture of data and structure, like a neural network, what we're doing is unifying the representation of structure, so the fact that that it may have certain layers in the neural network, data, such as the weights that we're trying to optimize, and the meaning, the fact that it is a neural network. And a lot of what we're doing then is building up the ontology of knowing that in a maths domain, things like times and plus are meaningful, and in a graphics domain, let's do a 2D graphic, things like lines and polygons are meaningful. Those are just specific domains of knowledge. Right, I promised to come back round to the AI kind of machine learning world. Now that we've got this sort of idea of the symbolic representation, how is that going to do something useful for us? Well, here's the workflow that I promised to automate. So this is kind of the standard workflow for any kind of modeling, but particularly for things like machine learning, is that we have a training stage where we model build. And we start with some data, and we have to do something to encode that from the real world. That might be a bunch of numbers, but it might be some words, or it might be some pictures or sound, and we have to turn that into something that the trainer can process. So typically that's encoding into numerical vectors. We then take a model, and there's lots of models out there, and we have to tune that model with some kind of training process so that it then represents the data, and then we're done with training, and we have a trained model. And then we sort of have to repeat the process with some new inputs that we actually want to predict against, encode that into the same way that we did before, using the same encoder, pass it through the trained model to get some prediction out, and then we have to decode that to make sense of that prediction vector to say, well, what does that mean in terms of the decision I make? So this is the workflow, and I kind of need to make that concrete now, so we ought to do some machine learning at this point. I imagine most of you were in yesterday's keynote where we saw the Titanic example, so I thought I'd repeat the same thing, but using this automatic workflow. So I think we can do this fast enough to do live. I'm going to get some data here. I'll call it T-data, and I'm going to use the exact data that we saw yesterday, which is the classic machine learning Titanic passenger data set. And we want only the training data portion. So here's the data, and you can already see that we've got kind of the ability to represent a nice rich structure here where we have a mixture of strings and numbers, and they're associated using this arrow notation with the outcome. So this is our inputs on the left, outputs on the right. Let's hide that data. We don't need to see that again. So now what we want to do is to do the task of classification. We want to put all of that data into classes of survival or died. Titanic equals classify of that, I called it T-data. And now the model training happens, and we get something back, and then we can use that thing and say Titanic of, and I would clearly travel first class. I'm 49 and male, and we will get our prediction out. And we could probably drill into that a bit deeper and find out why it's so pessimistic about me. Probabilities of that, and probability, this is the Achilles heel of live coding is spelling. Probabilities, is that right? There we go. Right, so there's our complete end-to-end workflow of train, build a model, apply the model, and get results out. But actually, hidden in the small print, there's a whole bunch of interesting things to point out here. This is really small, this font, so I'll read this to you. It says input type, nominal, numerical, nominal. I didn't tell it that. It's looked at the data, and because it knows about all kinds of data, and in this sort of symbolic world, all data is the same, I haven't had to tell it up front, here comes some text and some numbers and some text. It's inspected that and had a guess at what it's trying to do. And here it says method nearest neighbors. So it's gone and chosen that. The task I gave it was classification. And in fact, there's lots of ways. I could have used neural networks, or I could have used naive Bayesian, all of these different methods. But we're able to automate that so that it figures out by some heuristic and trial and error what's an appropriate method to apply. And that's only possible because we've got a really rich object that comes back. This is a symbolic representation of the trained classifier. So buried in the depths of this, and it's actually, if I showed the interior of it, it's quite large. There is both the fact that it's a classifier function, that it's used a particular method, what the training, the trained data is that's within that method, and then it's all represented in a way that is directly usable. And in fact, I stored this in a variable, just like any other piece of data, to be able to apply it. So when you've got a single dimension output, like you're trying to predict a number, or you're trying to predict a class, the problem is essentially solved. This is all you have to do at its simplest level. Now, of course, in practice, automation is not always as good as humans or just hard work. So sometimes you may want to get in there and take control. So if we repeat what the keynote speaker yesterday morning did, he used, let's say, method, and I think he uses decision tree, but I'm going to use gradient boosted decision tree. And we can force that method on it now. And you'll see, if you can read this font, gradient boosted trees is now the method. And I guess he actually went a bit further here and said max depth, is that the option? Forgive me if I can't remember correctly. He went to max depth of 3. OK, it's accepted that. So now we're replicating the exactly what he did yesterday. So one needs the ability to be able to control the methods and the hyperparameters. And there's probably 3 or 4 other hyperparameters I could set on this. But our assumption is that if we can automate that process, then not only have I saved myself a bunch of typing, and in many cases where the automation is good, it's still going to do the best job, I'm automating knowledge, because you don't need to know what are the different methods that I could choose. You don't need to know when, what the sort of appropriate hyperparameters are. If we can automate all of that, you can just say what your task is, which is I need to make a prediction. And because we've got this rich output object, then we're in a position to switch those methods, because the code is not sort of embedded in an unchangeable way that means I have to write completely different code in order to do a different kind of method. I can have that kind of embedded inside this richer object. And I'm afraid, as I was explaining to the organizers before I came on, my machine's gone a bit crashy in the last week. And I see the Mac spinning ball of doom here that says that I may need to quit this and just reopen it. Sorry about this. Hopefully, I spent the evening last night trying to diagnose what has happened to my poor machine. I can't even blame the new Mac operating system because I haven't upgraded to it yet. Let's go back to that. And see if we can get back into this. OK. Hopefully it'll only be once. We will see. So let's do a slightly different example now, which is I'm going to do something from computer vision. And at the face of it, this seems like a completely different kind of task. And what I'm going to do here is hopefully try and build a predictor for rock, paper, scissors. So I'm going to show it some examples here of rock, paper, and we'll get a few of these. And maybe that's enough. Let's do some scissors. And when we've got enough data, we can stop that. Now, this was just a little user interface to help me save some effort in capturing the data. So here's the data that we've got. I guess the first one, my camera didn't wake up in time. But what you can see here is we've got exactly the same kind of data structure. We've got an input and an output. And because all data is the same under symbolic computation, now I can simply say, well, give me the classification of that input to that output. And it's going to go away and do some thinking. And it's going to say, here we've got input type now is image. It's using logistic regression on image features. And hopefully, if this has done a good job, I can put the camera on here and put up rock, paper, scissors. Yeah, that's not too bad. Ooh, it's not too happy about rock or paper, but it's pretty clear on the rock and the scissors. So this sort of all data is the same suddenly makes the whole pipeline so much kind of less painful, because that automation of saying what's an appropriate encoder for an image is just part of the ontology of images. Now, I know some of you sat there going, yes, but what about real machine learning? Because when applying things to one-dimensional outputs, that there's half a dozen standard methods for, that's kind of the easy part. And it's true. The kind of richer machine learning is not fully automated yet. But there are still interesting things that symbolic computation can bring to the table if we look at the kind of higher dimensional outputs. Now, the basic problem is that as we go into high dimensional output, there's a lot more freedom about the way you might go about things. There are loss functions to decide, well, what is correct? When you've got very high dimensional output, that's not a sort of right or wrong answer like, did I predict died or survived correctly? Whether if I'm generating an image, if it's close to what I'm trying to generate, well, there's a lot of ways you can measure that. So we need a way of specifying those kinds of things to the system. And within the world of neural networks, the architecture of the neural network affects the task that it's capable of doing. There are architectures that are very good for image identification that are based around things like convolutional neural networks, and there are things like sequence predicting networks that need recurrent layers. So you actually need to be able to describe the architecture, and decode and encode is also rich as well. Now, whenever there's richness, you need a language. You need to be able to specify things as a human. But it turns out, just like being able to specify an equation symbolically, we can specify a neural network symbolically. And that turns out to be quite a useful step towards minimizing the work. So here's my sort of simplest neural network that I could think of that did something useful. And here's my symbolic description of it. Just like I might describe an equation in terms of power and plus, I'm describing a neural network in terms of a chain of 3 layers. So this is a linear, fully connected 20 layer, a non-linear tangent layer, a fully connected 1 layer, and then I'm specifying here the encoders and the decoders that are just going to be numbers. So I can enter that into the system, and it gives me a slightly more formatted version of it, but here's the representation of the network. Now, actually, behind the scenes, there's a whole bunch of things that I could have specified that I'm never going to do by hand. And so things like net-initialize have done that for me. It's filled it full of additional data about the weights and biases on the networks and set those up. So if we look at the thing internally, in fact, there's an awful lot of information in there. Well, quite a bit compared to what I typed. So the automation's already been able to kick in from this minimal, here's my human input, now give me the machine input on what the model looks like. And if we plot that thing, we'll see that it's essentially a random function because I initialize those weights with just some random numbers. So now I need to teach it to do something useful, and I want this to be an approximator to a sine function. Maybe sine isn't built in, and I need to do that from some data. So I'm generating here 120 points of data that say the sine of -6 is 0.27. And then the rest of the pipeline follows the same automation that I had before. I take the model. Now, instead of saying, pick one for me, I'm saying, use this model that I described, and I want to train it against the data. So it needs to do some thinking. And this is the loss function being shown, so we can see as the error goes down, it's getting more accurate. And eventually, when it's had a good think about that and looked at all the examples, we get a model out that is structurally the same, but it's got different internal data. And remember, in the symbolic world, data, meaning, and structure can all be embedded in a single thing. You don't have to break it up into different places. And let's have a look at the trained version of that, and it has done the job that we asked it. It now looks like it's making a decent approximation to the sine function. Now, even within that process, there's lots of opportunities to step in and spot automations that we can do. In fact, invisibly there was a training network was built around this that built an automatic loss layer because it was scalar in, scalar out. It was able to guess the loss layers that were needed for training, and it injected those. And things like encoding and decoding as well can sometimes be automated. So if I train this very simple thing against some different data, my network is even simpler here, but its data is some pictures going in and some Boolean values coming out. Oh, you're not going to go on me again, are you? It's the wheel of doom again. At least it's doing it on trivial things, not complicated things. Okay, this is annoying. But while it's thinking about that, oh, it's come back. Okay, you can see here that it's automatically picked image as an encoder and Boolean as a decoder. So I could have specified those things, but there's no point when it's obvious enough. And this decoding actually is very useful in terms of the workflow as well, because by having a good decode layer, we can return things into a format that are ready to compute. And so I promised some generative art. This is a network here that is for that. It's actually a bit more complicated. It's got 2 inputs, a style and a content, and both of those are images, and the decoder is an image as well. And this decoder of image is what makes it immediately useful, because if I grab myself a picture from my camera again here, there's a picture of me, and put that in as the content, and I style it against an example of Van Gogh, then hopefully what this will do is generate a Van Gogh of me in front of the podium. But the fact that it's got this decoder image means I can get this thing straight back in a form that's immediately usable. So I could do something like, I don't know, edge detect on that last answer with a 20-pixel radius and get the edges of that thing out, which I guess is kind of defeating the point of Van Goghing it. But so in order to make these things useful, this ability to transform between the different representations actually becomes very important. We don't want just back a bunch of RGB numbers in an array. And in fact, even within images, that's a complicated topic because you might think that an image is going to be RGB values, but it might not be. It might have an alpha channel, so it might have a fourth channel. It might be in CMYK color space or LAB color space. So actually having that kind of information encoded in the object that represents the image stops you making terrible mistakes of putting an LAB image in, using an RGB encoded neural network, making some prediction that in fact is completely wrong because the numbers just didn't represent what you thought they were. So once you've got this kind of symbolic representation, then it's just a case of mapping out the space of these are the layers that essentially, in the same way that sine, cos, and tan, and power and plus can map out the basics of maths, these are the layers that map out all of the basics of pretty much all the neural networks that are out there. And there's a few encoders that are built in, or I can encode my own. Now, at this point, I'm sure some of you are sat there going, great, CTC loss layer, excellent, I'm glad they've got that. And others of you are going, oh my God, there's so much to learn. So in order to encode these things from scratch, there is some domain knowledge to acquire, and I promised you automation. So the question is, how do we bridge this sort of chasm between needing lots of knowledge on architecture and being able to get on and do useful computations? So this is only partially an automation story, but a lot of it actually comes for free out of this symbolic representation of neural networks. So the first step is we need to give you examples. So we built this neural network repository, and at the moment it's just shy of 100 neural networks, and you can browse them by the kind of thing they apply to or the task. And so if I go to speech recognition, for example, there is one network, and here's a page about a network that is designed for turning speech to text. So by making that available, there's a kind of set of examples that you can work from. So the question is, what do you do with those examples? Well, the first is, use them. Our aim is that, and I think the way that a lot of the world is going is that there are sort of best-of-breed networks appearing for certain tasks. There are some very good networks out there for image identification, and if your image identification task isn't specialized, why not just use one of those off the shelf? So the idea is that we have a way of just fetching that directly from the repository into the system. And here is a classic one, which is the Learnet convolutional neural network for character recognition. And because all I've had to do is copy down that symbolic representation and store it, in this case in a variable called net, is now immediately available for me to apply. So I've got these images of digits, and I've managed to recognize them into numbers, and I could add those digits up, and now they're meaningful as numbers. So for a lot of cases, the idea is just find a net, fetch it, apply it within your code, and it's not your problem at all to get involved in the neural networks. They just behave like functions for doing fancy things. But typically, the problem in data science is you have to do something new. So the next thing you might want to do is to take something that is approximately right, but apply it in a new situation. And that is pretty much automated. So here I've taken that net for character recognition, and I'm giving it the Arabic for 7, and it doesn't know what to do with it. It was trained on Latin characters. So all I have to do is do what I did with my own network, which is to say net train on that net, because that net's in a very understandable form that the system knows what to do for processing. We can just do a net train on that, and let's stop that prematurely and apply it, and now it's learned that that's a 7. So where you've got the kind of same task but different numbers, that is a pretty automated process. Fetch the network, retrain it against new data. If you're ready to roll up your sleeves a bit, you can actually go somewhat further than that and adapt the network to a different task. So if we go back to this network, let's look at it here. You can see there's a bunch of layers like a convolutional layer. I don't know if this is readable here, but down at the bottom we see a linear layer size 10, softmax layer size 10. Now that's because it's a network designed for decoding numeric digits, 0 to 9. There's 10 of them. And so the linear layer and softmax layer are a combo for making a probability vector of which of 10 things it is. And there's a decoder to turn that into the digits. Now, if I wanted to make something that doesn't care about the digits, but it wants to say, is it Latin or Arabic characters, that 10 is a problem, because there aren't 10 languages. I've only got 2. But what I can do is I can treat the network just like any other piece of data. I can say, well, just give me the first 9 layers of that network and throw the rest away, just like I might take the first 9 elements of a list. And then I'm going to stick on two new elements, a linear layer 2 and a softmax layer, and it'll take care of the size inferencing in order to give me the final two layers being linear layer 2 and softmax layer 2. So I can do the kind of net surgery just to take off the bottom layers and swap in something slightly more useful without having to understand anything about how this convolution layer and ramp layer and pooling layer interact. And having done that, I can then retrain it, and I've got examples now that are just labeled Latin and Arabic. Oh, I guess I also had a decoder to say what my class names were. And after a bit of thinking, let's stop that early, we're making predictions about what language those characters are in. Now, I said at the beginning that the goal was an automated AI workflow. And I've spent a lot of time on the machine learning part, but actually the workflow is much longer. You've got to get data in, you've got to clean the data, you've got to do the modeling that we've just been talking about, you've got to validate the model, and then you've got to deploy it into production. And I know yesterday in the keynote that was talked about as possibly being roles for different people, but our view on automation is that one should automate it so that you can do the whole process yourself. Now, importing is pretty boring. I'm going to skip through connecting to databases, but I'm going to say a couple of things about cleaning, validation, and deployment quickly. And I think I'm running over on time, so let's just, well, let's do the thing that was talked about yesterday in the keynote, which was filling in things like the missing values. And because I quit this thing here, I need to, no, I can just do that. And it turns out machine learning can really help before you get to machine learning, bizarrely, because once you have these things kind of built into an integrated system, then you can start building useful tools on machine learning in order to apply machine learning to the process of cleaning, restructuring, validation, and so on. So in this example, as we saw yesterday, here's a problem that you didn't see when I did the classification earlier, because it was automated out of the way, but there was missing data in there. Now, yesterday's speaker said, well, let's figure out what the average is for a first-class male, and then fill that in. But actually, we can do better than that, because we can learn the entire distribution and then fill those in probabilistically. So we can actually get the entire spectrum of values, but weighted according to the way they exist. So by doing this learn distribution on the inputs, I'm actually learning about the shape of the data, so that then I can do synthesize missing values on those inputs. And, I didn't do what I meant to do here, which was to use the learn distribution I just did. It just relearned it on a small amount of data, but it's done approximately the same thing. It's figured out what a good approximate value or estimated value for that is based on the other values around it. So it's estimated that for a first-class male, 53.39 is a sensible age. And if I run that again, I'll get some other value, but on average, they kind of distribute over the same ranges, rather than locking them all into a single value, which as a median feels representative, but doesn't represent the shape of the distribution. So this is actually a kind of richer way of doing it. And we can also do things like detecting anomalies by the same kind of approach. Let's skip out of that, otherwise I'll run out of time, and talk about validation. So there's a couple of things that, again, can be totally automated here. That and I'm going to have to rebuild this because I quit, didn't I? And I did, let's do the short version, equals classify of, and it was example data of machine learning, Titanic training data. Right, let's just recreate that learner. So typically the task of measuring the performance is to compare it against unseen data. So just as the speaker did yesterday, we've got some test data that the classifier hasn't seen, and we want to compare that. Now, the expensive part of that is calling the machine learner over and over again on this data. And there's actually lots of different ways we could look at this. But we don't want to have to redo that comparison every time we look at a different property. So the idea is we do all of the computations once and then generate all of the measures simultaneously. Well, how do you represent all of these measures? Well, you want a rich object that is a symbolic representation of all of the measures. So this object here represents everything we now know about the performance of this. These are the kinds of things that we know, but I'm just going to show the headline things is that it was 77% accurate, and if we look at the breakdown of where it went wrong, we'll see that it did a very good job on predicting people who died, but actually for people who really survived, it's only about 50-50 that it's managed to predict whether they did or not. So that's the kind of really standard, compare the data against unseen examples. But actually, if you are more of an expert, this symbolic object actually yields other kind of much deeper insights, because since we've got a representation of the whole thing, and we've got a language that can compute with anything that is represented symbolically, we can reach into that and see what's going on inside it very easily. So here's a net model from the repository whose job is to do image identification. So I give it a picture, and it says tiger. And you can see this one's much more complicated. There's lots of layers, and some of these are graph layers that have sub-layers, and so there's a big, rich network I wouldn't necessarily want to do by hand. But as I said, I can reach into that thing and say, well, what's going on inside? Having trained the thing, I can extract the first layer, which was this very first convolutional layer. I can extract the weights, and then I'm going to do some visualization on those by saying, well, let's make an image of those and adjust it for brightness. And what this effectively does is it shows me the convolution choices that it's made. And if we look through this, we can probably see this looks like a convolutional layer that picks out horizontal lines. And this one looks like it's one that picks out diagonal lines, and who knows what this one is trying to do as sort of left-right half of the image measure. I don't know. I'd have to think about that one. Now, these things are quite hard to interpret, but they're there just to reach in and get. And if you want to see how it's actually handling it on a particular piece of data, well, that's also straightforward as well, because I can take this network, and just like any data, I can slice it and say, let's have the first layer of that. So I've just picked out it's still holding the training information, but I just picked out the beginning layer of this network. And now I can say, well, what happens to the output if we only ran the first layer? And let's turn those back into images. And what we see now is the kind of the thinking going on inside the network. This is what the network sees at layer 1, and this is the result of applying those convolutions. And we can see that some of these neurons seem to have found nothing of interest, others seem to have picked out lots of features. And if we go deeper into the network, then these things become increasingly abstract. And I don't know how deep I want to go here, but by layer 15, we're seeing things that probably nothing to do with the image and more about conceptual things that maybe they represent animalness or something completely abstract. So this all data is the same means that everything can be interacted with just like the numbers that you imported in the first place. And it also means that you can complete that kind of deployment workflow, because once you've got a symbolic representation of the network, we can copy that around. Well, if we can just describe things like user interfaces, then we can copy those around as well. So let's do that here. We'll make, let's do a really simple form page. So this is a symbolic description of a user interface. And I'm going to ask only one thing, which is a number, and then it's going to call the classifier that I built. And I'm only going to look at first class people of that age who are male, just to save my typing here. And a bit of syntax here, and there's my user interface. Not the prettiest user interface. I should probably spend more time putting a bit of narrative and styling on it. But the final step then is I want to make that thing available for other people. And I want to give it some permission structure here. I'm going to make it public so that you can use it right now. And I should have given it a name, but I didn't. But it's going to make one up for me, which is probably going to be really unhelpful. So it's made this cloud object with some very complicated name. But here now, in the cloud, is the symbolic representation, now rendered for HTML and JavaScript, and instead of in my notebook, with the classifiers being copied up so that I can click that button and get my prediction out. And maybe I could have made a visualization to make it a little bit more usable. So in the end, this whole workflow all stems on the fact that we have a constant representation that works in all of these different contexts. So I said our wider goal is automated computation workflow. And one of the things that is worth thinking about is that while the exciting stuff is machine learning at the moment, because it's made a lot of breakthroughs and it's solving problems that seemed intractable before, it's not the only game in town. And we're big believers in what we call multiparadigm data science, which is choose the method to suit the problem rather than just assume that we're going to hit it with machine learning because that's the only tool in our toolbox. So the thing is to have the ability then to mix and match and choose between tools. And my usual mantra is use machine learning when you're data rich and understanding poor. But the flip side of that is sometimes you understand stuff. And you don't want to use machine learning because that's kind of expensive on needing lots of data. And if you know about things, then use that human intelligence. And ideally, you want to mix things up. So I've brought a couple of examples that try to think of things that couldn't necessarily be solved in one or other domain, but require both. And this is a case of can we make a tool for taking an audio signal, and I'll display it here. So it's the sound of a car going past. Can we make a speed detector out of that? Now, if you had lots of samples of cars going past at known speeds, then you could just hit that with a machine learning problem if you're that data rich. I've got one sound here. And there's no off-the-shelf neural network for speed detection. But it turns out that machine learning is really good at one part of the problem, which is we can use this CREP network to pick out the frequencies. So here's the change in frequency as the vehicle passes us, and the Doppler shift makes it do that sound. And the machine learning does that much better, actually, than classical techniques. But then at the next step, it can't go any further. So we have to switch in to be able to take that and then compute with it by saying, OK, there is an algebraic problem, a little bit of Wikipedia time, and a bit of equation manipulation. I came up with this formula for Doppler shift, which I can then fit to that neural network output. And it's this ability to put them together that then allows us to get the parameter estimations for these out, and here's the insights that you get, that the vehicle's doing 20 meters a second, so about 40 miles an hour. And it turns out you can tell it came within 5 meters of the observer. Here's a problem that I worked with for a customer. The problem itself was kind of commercial, and it was about controlling customers. They come to a website, and you want to lead them to a high-value, high-margin product, or perhaps in a political context, you might want to lead them to some kind of story that you're trying to push. But you want to get them there subtly. You want to lead them only through things that are interesting to them. The obvious thing is put up a big advert that says, buy our expensive product. But imagine you're selling Ferraris, and they come to the bike searching for bicycles, searching for bikes. You want to say, have you thought of a car? Have you thought of a fancy car? Have you thought of a Ferrari? So this is the idea. Now, to solve that, there's actually a good mixture here. There's a feature extraction, feature distance measure that you need to generate using machine learning. But then after that, you end up with a network of relationships between how related is this page to the person's current interest, how related is that page, what's the shortest route across that network to the thing we want to get them to. So it's a mixture of graph theory and machine learning. Now, I can't show you the actual data, and frankly, it was pretty boring, so I made a proxy example, which is doing the same thing with dogs. And the idea is I have, actually, I'm not going to run all this. I have the Stanford Dogs database, and the feature extraction is just part of this automated pipeline of machine learning. So I can say, extract all the features that we know about these images. It doesn't know they're dogs. It's just looking for things they have in common. And then I have two controls over the graph that I get generated. One is to reduce the dimensionality. If you're in a really high dimensional space, there's always a shortcut through the middle, but we're flattening it down onto 2 dimensions. And then the shortest route is still direct connection between the points. So I'm punishing long distances by cubing the distance. And what you end up with is this is the graph of all of the dogs that I pulled in from the Stanford Dogs database. And now we can solve the shortest path. We're done with the machine learning. That was all in the feature extraction. And to make it interesting, I tried to pick the extreme dogs. So I found, I don't know which one I picked, this one and this one, but the ones that are the most distant across the network, and solved the shortest path. So it turns out that it's poodle with a duck in its mouth through to chow chow is the longest, shortest path. But you can see now visually the effect of this process, that we start with a poodle, we go to a poodle with shorter hair, another short-haired poodle, a short-haired poodle that's dark, now some dark dogs, and we end up in Alsatians and then Huskies, and then eventually we make the transition through to the target chow chow lying in a field. So conceptually, it's the same thing as my website navigation problem. It just happens to be with pictures instead of text. So to wrap up, hopefully you've seen some of the things that are in our belief system about the way we build software, which you should transfer even if you aren't interested in our tech. More automation is always important. Unless your tool is completely hidden behind the scenes. If you're going to let other people use code you're writing, the more you automate, the better, because it automates all of those knowledge things that you have that you seem easy to use, but ease of use is all about automation, as well as actually making it quicker to use. And in the end, having the richest data structure, even though it seems complete overkill for the data you're holding, is the long-term thing for being able to join things up, because you can always drop from a rich data structure to a simple one. You can always kind of flatten information or aggregate. You can never go back. So once you've told that you've built your architecture around numerical matrices, there's no going back to automating that that's an image or that's a sound or whatever. And in the end, the doing the AI isn't going to be the value. Right now, if you have expertise in AI, you're extremely valuable, but that's not the long term, because automation is only ever going to go up. The value is in that whole workflow from beginning to end, and having that understanding of the workflow in order that you can join things up in a way that is useful for the problems that you're dealing with. So I hope that's been, I know you all came here for content. I hope that was some satisfying content. You can access the talk online off this address or this QR code, and I believe we have some time for some questions.